Picture this. It is dawn in Rome. The year is 126 AD. The air hangs thick with the scent of volcanic ash and lime, mingling with the sweat of 10,000 workers. Before you rises a structure so audacious, so impossibly ambitious, that even the gods themselves might pause in wonder. The Pantheon, a temple to all gods. Its dome, a perfect hemisphere of concrete, spans 143 feet across, wider than any dome built before or for 17 centuries after. The architect, whose name history has swallowed into silence, stands at the centre of this architectural marvel. He looks upward through the oculus, that perfect circular opening at the dome's crown, where a shaft of golden morning light descends like a divine finger pointing toward eternity. He knows something we have forgotten. He understands something we have lost. This concrete will not crumble. It will not crack. It will not surrender to the relentless assault of time. 2,000 years later, we stand in the shadow of that same dome, still perfect, still whole, still defying every law of entropy we think we understand. Meanwhile, our modern concrete highways crack within decades. Our bridges require constant repair. Our tunnels leak. Our dams weaken. How is this possible? What did the Romans know that we have forgotten? Tonight, we embark on a journey that will take us from the volcanic mountains of Pozzuoli to the underwater harbours of Caesarea, from the scrolls of Vitruvius to the electron microscopes of Berkeley, from the glory of an empire that spanned the known world to the humble rediscovery of secrets hidden in plain sight for 2 millennia. This is not merely a story about concrete. This is a story about human ingenuity, about the tragic loss of knowledge, about the arrogance of modernity, and about the humbling moment when we realize that our ancestors, whom we often dismiss as primitive, possessed wisdom that took us 2,000 years to even begin to understand. The Romans built structures that have outlasted empires, religions, languages, and civilizations. They constructed underwater harbours that marine biologists now study because the concrete has created thriving ecosystems. They erected domes that architects still cannot fully replicate without modern steel reinforcement. And then, the knowledge vanished. Like so much of ancient wisdom, the precise formula, the exact proportions, the subtle techniques passed from master to apprentice. All of it dissolved into the mists of the Dark Ages. Libraries burned. Masters died without successors. The oral traditions that preserved these secrets for generations were severed by war, plague, and the collapse of the greatest civilization the Western world had ever known. For over 1,000 years, humanity forgot how to build like the Romans. We built cathedrals that required flying buttresses because we could not span spaces the way they did. We constructed harbours that eroded within generations because we did not understand their maritime concrete. We laid roads that fractured under frost and heat because we lost their recipe for resilience. It is one of history's most profound ironies. We call ourselves advanced, sophisticated, technologically superior. We have split the atom, walked on the moon, and mapped the human genome. Yet we cannot, or could not, until very recently, match a building material perfected by engineers 2,000 years ago who worked without computers, without chemical analysis, without modern tools. This humbling reality forces us to confront uncomfortable questions about progress itself. Is history truly a linear march toward enlightenment? Or is it a cycle of rise and fall, wisdom and forgetting, discovery and loss? Have we, in our rush toward the future, left behind knowledge that might have carried us further, faster, more sustainably? The story of Roman concrete is the story of human civilization in miniature. It contains within it all the themes that define our species: ingenuity and innovation, hubris and humility, loss and rediscovery, the eternal tension between what we know and what we have forgotten. Tonight, You will discover why a 2,000-year-old harbour in Israel holds secrets that could revolutionise modern construction. You will learn how volcanic ash from a bay near Naples became the foundation of an empire. You will understand why Roman concrete actually grows stronger with time, performing a chemical magic trick that modern science is only now beginning to comprehend. But more than that, you will feel the weight of lost knowledge. You will sense the ghostly presence of Roman engineers whispering across the centuries. You will experience the thrill of rediscovery, as modern scientists piece together clues like archaeologists of chemistry, excavating not ruins, but molecular structures, uncovering not artifacts, but atomic bonds. This is the lost blueprint, the forgotten formula that built an empire and outlasted it by 1,500 years. Are you ready to uncover what was lost? Then let us begin. At the beginning. When gods walked among volcanic ash, to understand Roman concrete, we must first travel backward in time to a place where the earth itself seemed alive with divine power, the Bay of Naples, 3rd century BC. The Greeks who settled here called it Campi Flegrei, the fortunate countryside. They were not wrong. The volcanic soils produced wine so exquisite that wealthy Romans would pay fortunes for a single amphora. The climate was Mediterranean perfection. The natural harbours welcomed ships from across the known world, but beneath this paradise, something darker stirred. The supervolcano we now call the Campi Flegrei, the Phlegræan fields, had erupted 39,000 years ago with such violence that it plunged Europe into volcanic winter and nearly drove humanity to extinction. That explosion was 500 times more powerful than Mount St. Helens. It ejected enough material to bury all of Los Angeles under a layer of ash 100 feet thick. For the ancient Greeks and Romans who lived atop this sleeping giant, the landscape was one of supernatural unease. Fumaroles hissed with sulphurous breath. Hot springs bubbled with water that could boil flesh. The ground itself rose and fell like the chest of some sleeping titan, a phenomenon geologists now call bradyseism, the slow breathing of the earth. The Romans believed this place was the gateway to the underworld. They thought the mythical river Styx flowed through underground caves here. They whispered that on certain nights, if you listened carefully, you could hear the moans of the damned. But the Romans, pragmatic as always, also noticed something else: the ash, the particular kind of volcanic ash that covered the region. There was something unusual about it. When mixed with lime and water, it did not merely harden, it transformed. It became something stronger than stone, more durable than marble, more resistant to time than bronze. They called it pulvis puteolanus, the powder of Puteoli, named after the town we now know as Pozzuoli. Today, we call materials with similar properties Pozzolanic, a direct linguistic descendant of that ancient Roman discovery. But how did they discover it? Imagine a Roman engineer in the 3rd century BC, perhaps overseeing the construction of a simple wall. Standard practice would be to use stone blocks mortared together with lime paste. Lime, produced by heating limestone, was the universal binding agent of the ancient world. But pure lime has limitations. It sets slowly, it remains relatively weak, and it cannot cure underwater at all. But here in Campania, something different happened. Perhaps by accident, perhaps through systematic experimentation, Roman builders began mixing the local volcanic ash into their lime mortar. The results must have seemed miraculous. The mixture set faster, it hardened stronger, and most remarkably, it could be poured underwater and would actually cure beneath the waves, something impossible with pure lime. This was not just an incremental improvement, this was a revolution. Imagine the moment of realization. Some unnamed Roman engineer standing in a harbour, watching a submerged portion of his concrete construction harden beneath the sea, understanding in that instant that his people had stumbled upon something that would change history. With this discovery, Rome could build harbours anywhere. They could construct aqueducts that would carry water across mountains and valleys. They could erect structures of unprecedented size and daring. They were no longer limited by the constraints that had bound every previous civilization. The first master to systematically describe this knowledge was Marcus Vitruvius Pollio, a Roman architect and engineer who served under Augustus Caesar in the 1st century BC. His treatise, De Architectura, on architecture, is the only surviving major work on architecture from classical antiquity. In Book 2, Chapter 6, Vitruvius writes with the precision of a scientist and the poetry of a philosopher. There is also a kind of powder which from natural causes produces astonishing results. It is found in the neighbourhood of Baiae and in the countryside belonging to the towns around Mount Vesuvius. This powder, mixed with lime and rubble, not only lends strength to buildings of other kinds, but even when piers are constructed of it in the sea, they set hard underwater. Vitruvius understood that he was describing something extraordinary. He knew that this material gave Rome a strategic advantage. Control of Pozzolanic ash meant control of the Mediterranean, because only Rome could build the massive harbour works required for naval supremacy. But Vitruvius also understood something deeper. He recognized that this material worked through principles that transcended human understanding. He wrote about it with reverence, as if the gods themselves had gifted this knowledge to humanity. And in a sense, they had. The violent convulsions of the earth, the apocalyptic eruptions that created this ash, these were forces beyond human control or comprehension. The Romans simply had the wisdom to observe, experiment, and harness what nature provided. The formula they perfected was elegant in its simplicity: volcanic ash, lime, seawater, and aggregate. 4 ingredients, mixed in specific proportions that varied depending on the application. Add more ash for underwater construction. Use different aggregates for different strengths, brick fragments for lighter domes, dense basalt for foundations, even pumice for dramatic weight reduction in soaring vaults. The process was labour-intensive, but not complex. Workers would pulverize the volcanic ash into a fine powder. Lime would be prepared by heating limestone in massive kilns that burned for days. These 2 materials would be mixed dry, then combined with water and aggregate, poured into wooden formwork, and allowed to cure. But here is where the magic happened, where modern concrete reaches its maximum strength within weeks and then begins a slow process of decay. Roman concrete continued to transform and strengthen over years, decades, even centuries. The Romans did not understand why. They could not peer into the molecular structure of their material. They could not analyze the chemical reactions with instruments of precision. They simply knew, through empirical observation and generations of accumulated wisdom, that their concrete worked, and work it did. The Pantheon, completed in 126 AD, still holds the record as the world's largest unreinforced concrete dome. Its oculus is 30 feet across, open to the sky, allowing rain to fall directly into the temple. For nearly 2,000 years, rain has fallen through that opening. For nearly 2,000 years, the concrete has endured. The markets of Trajan, a massive multi-level shopping and administrative complex completed in 113 AD, utilized concrete vaulting on a scale that would not be matched until the Industrial Revolution. Roman engineers poured concrete into sophisticated formwork to create barrel vaults, groin vaults, and hemispherical domes that distributed weight in ways that allowed for vast interior spaces without internal supports. The baths of Caracalla, completed in 216 AD, covered 27 acres and could accommodate thousands of bathers simultaneously. The complex required massive concrete structures to support pools, heating systems, and soaring vaulted ceilings. These structures still stand, testament to engineering mastery. But perhaps most impressive were the harbour works. The port of Caesarea, constructed by Herod the Great between 22 and 10 BC, was one of the largest engineering projects of the ancient world. Herod, client king of Rome, wanted to transform a coastline with no natural harbour into a massive maritime complex that would rival Alexandria. The challenge was enormous. The Mediterranean coast of Judea offered no protected bays, no natural promontories. Everything would have to be built from scratch and built underwater in one of the most hostile marine environments in the world. Roman engineers designed massive breakwaters using the underwater concrete technique. Wooden formwork was floated into position and sunk. Then concrete was poured directly into the seawater, where it would cure beneath the waves. The breakwaters extended hundreds of feet into the Mediterranean, creating an artificial harbour large enough to berth dozens of large vessels. This harbour functioned for centuries. Even after earthquakes damaged portions of the breakwater, even after the empire fell and maintenance ceased, the concrete remained. Modern marine archaeologists diving among the ruins have discovered something astonishing. The concrete has not merely survived, it has created its own ecosystem. Minerals crystallizing within the concrete have formed structures that attract marine life. The Roman concrete has become quite literally part of the living ocean. The Romans built harbours across the Mediterranean using these techniques. Portus, the massive harbour complex that served Rome itself, covered 200 acres and featured inland artificial basins connected to the Tiber River by canals. Leptis Magna in North Africa, Alexandria in Egypt, Piraeus in Greece. Wherever Rome needed to project power across water, their concrete made it possible. And then there were the roads. While Roman roads are famous for their stone paving, less well known is that many of these roads had concrete foundations. The Via Appia, the Queen of Roads, stretched from Rome to Brundisium on the heel of Italy's boot, a distance of 350 miles. Sections of this road, built beginning in 312 BC, can still be walked today, their concrete foundations as solid as the day they were poured. The aqueducts, those magnificent structures that carried fresh water across vast distances, relied heavily on concrete. The Aqua Claudia and Aqua Annio Novus, completed in 52 AD, carried water nearly 50 miles from mountain springs to Rome. Much of this distance was underground or supported by massive concrete arches that still stride across the Roman countryside. These were not merely utilitarian structures, they were statements of power, demonstrations of capability, monuments to human ingenuity. The Romans understood that engineering was inseparable from civilization itself. To build greatly was to be great. But there was something more, something the Romans understood instinctively but could not articulate scientifically. Their concrete was alive. Not literally, of course, but in a sense more profound than mere metaphor. The chemical reactions that occurred within Roman concrete continued for decades, for centuries. The material evolved, it adapted. In the presence of seawater, it actually healed itself, filling cracks with new crystalline growth. Modern concrete is dead from the moment it cures. It reaches its maximum strength and begins inevitable decay. Freeze-thaw cycles crack it. Salt intrusion corrodes it. Chemical attack weakens it. Within 50 years, most modern concrete structures require significant repair or replacement. Roman concrete, by contrast, grows more complex with age. Like an old-growth forest developing layer upon layer of ecological complexity, Roman concrete develops increasingly intricate crystalline structures that reinforce its matrix. The Romans recognized this empirically. They knew that structures grew stronger with time. They built accordingly, with confidence that their works would outlast dynasties. And here lies the first great tragedy of our story. This knowledge, so painstakingly developed, so carefully refined, so thoroughly proven, was lost. When the Western Roman Empire collapsed in 476 AD, it took with it not just political unity, but technological continuity. The networks of knowledge that connected masters to apprentices across the empire fractured. The great engineering schools closed. The systematic documentation that men like Vitruvius had begun was abandoned. The Eastern Roman Empire, based in Constantinople, preserved some of this knowledge. Byzantine builders continued to use sophisticated concrete and mortar techniques for centuries. The Hagia Sophia, completed in 537 AD, utilized advanced materials science in its construction. But even in the East, the precise Roman formulations were eventually forgotten. The volcanic ash of Pozzuoli was far away. Local materials had to substitute. The old mastery faded. In the West, the knowledge disappeared almost entirely. Medieval builders in Europe worked primarily in stone and timber. They built magnificent cathedrals, but these required entirely different structural principles: flying buttresses, pointed arches, massive walls to contain lateral thrust. No medieval builder could have constructed the Pantheon. The knowledge was gone. For over 1,000 years, humanity forgot how to make Roman concrete. This loss was not unique. The ancient world possessed numerous technologies and knowledge systems that vanished in the chaos of the Dark Ages. Greek fire, the Byzantine naval weapon that burned on water, was lost. The precise method of making Damascus steel was lost. The astronomical calculations of the Antikythera mechanism were lost. But the loss of Roman concrete is particularly poignant because we continued to build. We continued to need durable structures. We continued to struggle with the same problems the Romans had solved, and their solutions stood before us, mocking our ignorance. Every time a medieval mason looked at the Pantheon, he was looking at knowledge he could not access. Every time a Renaissance architect marveled at Roman aqueducts, he was confronting the limits of his own understanding. The Roman ruins scattered across Europe and the Mediterranean were not just monuments to a fallen empire. They were libraries written in stone and concrete, filled with information we could no longer read. 1,000 years of darkness and rediscovery. The medieval stonemason stands before the Pantheon, late afternoon sun slanting through the oculus, illuminating motes of dust that dance like memories in the golden light. He has travelled from Florence, commissioned to study ancient building techniques that might inform the construction of a new cathedral. He runs his hand across the concrete dome, smooth, intact, without crack or fissure despite standing for over 1,000 years. He knows the mathematics of his own time, the careful calculations of thrust and counterthrust, the delicate balance of weight and support that allows Gothic cathedrals to soar. But this is different. This is a continuous shell, a hemisphere spanning a space his master builders could not match, even with all their flying buttresses and pointed arches. This dome is unreinforced, no hidden framework, no secret support structure, just concrete poured into formwork nearly 13 centuries before he was born. He does not understand how it was made. He cannot replicate it. He can only wonder and move on. This scene, repeated across centuries, encapsulates the tragedy of lost knowledge. The answer was right there, literally written into the structure of buildings that still function perfectly. But without the conceptual framework to understand what they were looking at, without the chemical knowledge to analyze the materials, without the historical records to guide them, medieval and Renaissance builders were as baffled by Roman concrete as we might be by alien technology. Some tried to rediscover it. In the 15th century, Leon Battista Alberti, the great Renaissance architect and humanist, studied Vitruvius obsessively. He measured Roman buildings. He analyzed their proportions. He attempted to extract principles that could guide modern construction. Alberti recognized that the Romans had possessed systematic knowledge, not merely practical tricks. In his own architectural treatise, De Re Aedificatoria, consciously echoing Vitruvius, he wrote with frustration about techniques he could admire but not fully comprehend. He understood that Roman concrete involved volcanic ash. He knew that this ash came from Pozzuoli. But the precise proportions, the specific techniques, the subtle variations for different applications, these remained elusive. Andrea Palladio, in the 16th century, perhaps the most influential architect of the Renaissance, also studied Roman structures intensively. He made careful drawings of ancient buildings, trying to understand their structural logic. His own work, brilliant though it was, relied primarily on stone construction. He could not match Roman spanning capabilities. The gap between admiration and understanding can be unbridgeable without the right tools. Medieval and Renaissance builders were like scholars trying to read hieroglyphics before the Rosetta Stone. They could see that meaning was there, encoded in the text, but they lacked the key to unlock it. Part of the problem was material. The volcanic ash that made Roman concrete possible was geographically limited. If you were not building near Pozzuoli or Vesuvius or other volcanic regions with similar ash deposits, you simply could not access the right materials. But the deeper problem was conceptual. Pre-modern chemistry could not explain why volcanic ash worked. Without understanding the molecular reactions, without grasping concepts like hydraulic binding or Pozzolanic activity, even someone who had the ash could not use it optimally. This is a recurring pattern in the history of technology. We can often use techniques we do not fully understand, passing them down through apprenticeship and tradition. But when that chain of transmission breaks, rediscovery without theoretical understanding is nearly impossible. Think of it this way. If civilization collapsed tomorrow and all written records were lost, future archaeologists might find smartphones. They might even figure out how to charge them if they found solar panels. But could they manufacture new ones? Could they understand the semiconductor physics, the software architecture, the complex supply chains that make such devices possible? Roman concrete is our smartphone from the past, a technology so sophisticated that even when we could examine it, even when surviving examples surrounded us, we still could not replicate it for centuries. The Age of Enlightenment brought new approaches. The scientific revolution of the 17th and 18th centuries created frameworks for systematic investigation. Chemistry emerged as a discipline. Materials could be analysed, tested, their properties quantified. In the 18th century, British engineer John Smeaton was tasked with building a lighthouse on the Eddystone Rocks, a treacherous reef off the coast of Cornwall. Previous lighthouses had been destroyed by storms. Smeaton needed a building material that could withstand the savage assault of the Atlantic. He began experimenting with different types of lime mortar. He tested various additives, and he discovered, through trial and error, that lime mortars mixed with certain kinds of clay would set harder and resist water better than pure lime. He did not know it at the time, but he had rediscovered a principle of hydraulic cement, the same principle that made Roman concrete work. The clay he was using contained some of the same aluminum and silicon compounds found in volcanic ash. Smeaton's work was groundbreaking, but it was still empirical. He knew what worked. He did not know why. The true revolution came with Portland cement. In 1824, British bricklayer Joseph Aspdin patented a new artificial cement that he called Portland cement, because its colour resembled the prestigious Portland stone used in British construction. Aspdin's process involved heating limestone and clay together, then grinding the resulting clinker into a fine powder. This was not Roman concrete. The chemistry was different. The properties were different. But it was the first modern attempt to create a hydraulic cement through systematic industrial processes, rather than relying on natural volcanic materials. Portland cement would eventually become the foundation of modern concrete. By the late 19th century, it was being produced industrially. By the 20th century, it had become one of the most widely used materials in human history. Today, we produce over 4 billion tonnes of Portland cement annually. But here is the bitter irony. Portland cement, for all its utility, for all its versatility, for all its ubiquity, is in crucial ways inferior to what the Romans made 2,000 years ago. Modern concrete is stronger initially. It cures faster. It is more standardized and predictable. These are real advantages for modern construction, where time is money and consistency is essential. But modern concrete also deteriorates faster. It cracks more easily. It cannot heal itself. And it is catastrophically unsuitable for marine environments, the very application where Roman concrete excelled. Consider modern harbour infrastructure. Concrete exposed to seawater faces multiple forms of attack. Salt water infiltrates the material. Chloride ions corrode steel reinforcement. Freeze-thaw cycles cause spalling. Chemical reactions weaken the cement matrix. The result? Modern marine structures require constant maintenance. Harbours must be repeatedly repaired. Offshore platforms have limited lifespans. The economic cost is enormous. Billions of dollars annually spent on repairing or replacing concrete structures damaged by seawater. Meanwhile, Roman harbour works, built 2,000 years ago with no steel reinforcement, no modern admixtures, no epoxy coatings, continue to sit in the Mediterranean, structurally sound, supporting ecosystems, outlasting the civilization that created them. This is humbling. Deeply humbling. We live in an age of unprecedented technological capability. We can synthesize materials at the atomic level. We can model chemical reactions with quantum precision. We can manufacture products to tolerances measured in nanometers, and yet we built the entire modern world on a type of concrete that is fundamentally less durable than what ancient engineers created using volcanic ash, lime, and seawater. Why did this happen? Partly, it is a question of priorities. Modern concrete was optimized for rapid construction, high early strength, and consistency. These are the demands of industrial society. The Roman approach, slower curing, more time-intensive production, reliance on specific geological materials, does not fit well with modern construction economics. But there is something deeper here, something about the nature of progress itself. We assume that newer is better, that later civilizations automatically surpass earlier ones, that the arrow of technological development points inexorably upward. This assumption is so deeply embedded in modern thinking that we rarely question it. Yet history repeatedly demonstrates that progress is not linear. Knowledge can be lost. Capabilities can regress. Civilizations can fall from heights they do not reach again for centuries. The Romans could build harbours we cannot match. Medieval Europeans could create stained glass, whose colours we still cannot fully replicate. Renaissance artists developed painting techniques lost to later generations. The Industrial Revolution destroyed craft traditions that preserved knowledge about materials and methods that took centuries to redevelop. Each of these represents a discontinuity, a break in the chain of knowledge transmission that required later rediscovery. Roman concrete is simply the most architecturally visible example of this phenomenon. But it is not unique. For over a century after Portland cement became dominant, very few people even asked why Roman concrete lasted so long. It was ancient. It was obsolete. It was irrelevant to modern construction. Why bother studying it? This attitude began to change in the mid-20th century, particularly after World War II, when many ancient structures were damaged and required restoration. Archaeologists and engineers studying Roman buildings began to realize that the concrete in these structures had properties that modern materials could not match. But understanding why required tools that did not exist until recently. You cannot understand Roman concrete with the naked eye. You need to peer into its molecular structure. You need electron microscopy. You need X-ray diffraction. You need mass spectrometry. You need computational chemistry to model reactions that occur over centuries. All of these tools emerged in the late 20th and early 21st centuries. And when scientists finally turned them toward Roman concrete, what they discovered was astonishing. Marie Jackson, a geologist and engineer at the University of California, Berkeley, became obsessed with Roman concrete in the early 2000s. She had a background in volcanic rocks and cement chemistry, the perfect combination for understanding what the Romans had created. Jackson led expeditions to ancient Roman harbour sites. She took cores of concrete from underwater structures at Portus, near Rome, and from the harbour of Caesarea in Israel. These samples, extracted from breakwaters that had been submerged in seawater for 2 millennia, became the subjects of intensive analysis. What her team discovered reads like a detective story where the detective is examining evidence at the molecular level. Under electron microscopy, Roman concrete revealed an incredibly complex internal structure. Rather than the relatively homogeneous matrix of modern concrete, Roman concrete was full of unusual crystalline formations. Some of these crystals were minerals that do not form in modern concrete at all. The key discovery involved a rare mineral called aluminum tobermorite. Tobermorite is a calcium silicate hydrate, part of the family of compounds that form when cement reacts with water. But aluminum tobermorite is special. It forms only under specific conditions of temperature and chemical composition. It is extremely stable, and it grows over time through interaction with seawater. Here is what was happening. When Roman concrete was immersed in seawater, a remarkable chemical dance began. The volcanic ash in the concrete contained significant amounts of silica and aluminum. The lime in the concrete provided calcium and created an alkaline environment. The seawater provided sodium, potassium, magnesium, and other dissolved ions. These ingredients, under the gentle heat of the Mediterranean sun, began a slow reaction that would continue for centuries. Seawater penetrated the concrete through tiny pores. Rather than corroding it, as seawater corrodes modern concrete, it triggered the growth of new minerals. Aluminum tobermorite crystallized within the concrete matrix, filling microscopic cracks and voids. This created a self-healing mechanism. Damage to the structure actually stimulated repair at the molecular level. Even more remarkably, this process strengthened the concrete over time. The crystalline growth created an increasingly interlocked, increasingly dense material structure. Roman concrete did not just resist decay, it actively improved with age. This was the secret the Romans could observe but not explain. They knew their harbour works grew more durable with time. They did not know about aluminum tobermorite or Pozzolanic reactions or X-ray diffraction. They simply built with empirical confidence in materials they had perfected through generations of trial and error. Modern science finally understood what they had done, but understanding created new challenges. Could we replicate it? Should we try to recreate Roman concrete for modern use? What would it take to bring this ancient technology into the contemporary world? These questions are more complex than they might appear. The volcanic ash the Romans used is not a standardized commodity. Different deposits have different chemical compositions. The ash from Pozzuoli is not identical to ash from Vitruvius or from volcanic regions in Turkey or Greece, where Romans also sourced materials. Modern concrete manufacturing relies on precise, consistent inputs. Portland cement is produced to exacting chemical specifications. Aggregates are graded and sorted. Admixtures are carefully formulated. This standardization is what makes modern construction possible at global scale. Roman concrete, by contrast, required craftsmen who understood materials intimately, who could assess the quality of ash by eye and touch, who knew how to adjust proportions for different applications, who possessed tacit knowledge that could not easily be codified into specifications and building codes. This presents a fundamental challenge. Can we industrialize a craft tradition? Can we standardize an artisanal process? Can we translate knowledge developed through apprenticeship into knowledge that can be taught in engineering schools and implemented by construction companies? Some researchers are trying. Teams around the world are experimenting with creating concrete using volcanic ash or synthetic materials that mimic its properties. Others are investigating whether industrial byproducts, fly ash from coal plants for instance, might serve similar Pozzolanic functions. There are promising signs. Some experiments have produced concrete with self-healing properties similar to Roman formulations. Some test structures show improved resistance to seawater, but we are still in the early stages of rediscovery. And this raises profound questions about our relationship with the past. For centuries, we viewed ancient civilizations as primitive precursors to our own enlightened modernity. We studied them as historians and anthropologists, not as engineers and scientists from whom we might learn practical techniques. The rediscovery of Roman concrete's superiority forces us to reconsider this attitude. It suggests that ancient peoples working within their own contexts sometimes achieve solutions to problems that we, for all our sophistication, have yet to match. This is simultaneously humbling and inspiring. Humbling because it reveals the limitations of our own knowledge, the gaps in our technological traditions, the ways in which progress can mask regression. Inspiring because it suggests that somewhere in the archaeological record, somewhere in the ruins of past civilizations, there may be other lost techniques, other forgotten knowledge, other solutions waiting to be rediscovered. Revelation and Renaissance. Let us return to the shores of the Mediterranean. But this time, we are not looking backward at crumbling empires. We are looking forward to harbours yet to be built, to structures that might stand for millennia, to a possible future where we finally reclaim what was lost. The revelation of Roman concrete's secrets represents more than just an interesting historical footnote. It represents a potential revolution in how we build our world. Consider the scale of the challenge facing modern civilization. We have built our entire industrial infrastructure on materials that have designed obsolescence. Our concrete highways, bridges, dams and buildings deteriorate on predictable timelines. We know this. We plan for it. We budget for endless cycles of repair and replacement. This is not sustainable. China alone poured more concrete between 2011 and 2013 than the United States poured in the entire 20th century. The developing world is building cities at a pace unprecedented in human history. If all of these structures have 50-year lifespans, we face an endless treadmill of demolition and reconstruction. The environmental costs are staggering. Cement production accounts for approximately 8% of global carbon dioxide emissions, more than the entire aviation industry. The resource consumption is equally vast. Concrete is the second most used substance on Earth after water. What if there was another way? What if we could build structures that lasted not 50 years, but 500? Not a century, but 2 millennia? What if our harbours self-healed? Our bridges grew stronger with time. Our buildings became more durable with age. This is the promise hidden in Roman concrete. Marie Jackson and her colleagues at Berkeley have been working to understand not just how Roman concrete works, but how its principles might be applied to modern construction. Their research has revealed several key insights. First, the slow-curing nature of Roman concrete, often seen as a disadvantage in modern construction, is actually crucial to its long-term durability. The gradual chemical reactions allow for the formation of complex crystalline structures that would not develop in rapidly setting modern concrete. Speed has a price, and that price is permanence. Second, the incorporation of volcanic ash creates a material that is chemically reactive in beneficial ways. Rather than being inert once cured, Roman concrete continues to interact with its environment, particularly in the presence of seawater. This ongoing reactivity enables self-healing and progressive strengthening. Third, the Romans built without steel reinforcement. Modern concrete relies heavily on steel rebar, which corrodes in marine environments and causes catastrophic structural failure. Roman concrete, being unreinforced, cannot fail in this way. It is monolithic, unified, without the internal contradictions that plague modern reinforced concrete. These insights are leading to practical applications. Several experimental projects are now underway. In Italy, researchers are constructing test structures using recreated Roman concrete formulations. In the United States, the Department of Energy is investigating whether Roman concrete principles could be applied to nuclear waste containment, a critical application where durability over thousands of years is essential. Most ambitiously, there are proposals to use Roman concrete techniques for marine infrastructure. The ocean economy is growing. Offshore wind farms, aquaculture facilities, artificial reefs, floating cities, all of these require durable materials that can withstand the harsh marine environment. Imagine breakwaters constructed using Roman methods, designed not just to withstand the ocean, but to improve with exposure to it. Imagine artificial reefs that do not degrade, but actually become more structurally sound over centuries while supporting marine ecosystems. Imagine harbour works that require no maintenance, that need no repair, that simply function decade after decade, century after century. This is not fantasy. This is rediscovered reality. But the implications extend beyond construction. The story of Roman concrete teaches us something profound about knowledge itself. We live in an era of information abundance. We have access to more data, more research, more accumulated knowledge than any previous generation in history. We assume that this ensures progress, that having more information means knowing more. But information is not knowledge. Data is not wisdom. Having access to facts does not mean understanding how those facts fit together into actionable frameworks. The Romans knew how to make superior concrete, not because they had more information, but because they had integrated tacit knowledge, knowledge embedded in practice, in craft tradition, in the accumulated experience of generations of builders. This type of knowledge is fragile. It does not survive well in written form. It requires continuity of tradition, master to apprentice transmission, hands-on experience. When that chain breaks, the knowledge evaporates, even if written descriptions survive. Vitruvius described Roman concrete techniques, but reading Vitruvius did not enable Renaissance architects to replicate them. The written word preserved the fact of the knowledge, but not the knowledge itself. This distinction is crucial in our current moment. We are digitizing everything, creating vast archives of information, assuming that this preserves knowledge for future generations. But are we capturing the tacit knowledge, the embodied skills, the subtle understanding that comes only through practice? If our civilization were to collapse tomorrow, could future archaeologists reading our technical manuals actually rebuild our technology? Or would they face the same challenge medieval masons faced looking at the Pantheon, able to see what was accomplished, but unable to understand how? The rediscovery of Roman concrete demonstrates that lost knowledge can be recovered, but only with immense effort, using tools and frameworks that may not exist for generations. How much easier it would have been if the knowledge had never been lost in the first place. This realization has sparked what some scholars are calling a revival of craft epistemology, a recognition that hands-on practical knowledge is valuable not just for antiquarian interest, but for solving contemporary problems. Around the world, programs are being established to study traditional building techniques, not as museum pieces, but as potentially superior solutions to modern challenges. Architects are experimenting with ancient methods of passive cooling and heating. Engineers are investigating traditional water management systems. Materials scientists are analysing ancient alloys and ceramics. Some of these investigations reveal that traditional methods were simply the best available at the time, now superseded by modern alternatives. But others, like Roman concrete, proved to be genuinely superior for certain applications. This creates a paradigm shift. Instead of viewing history as a story of steady progress from primitive to advanced, we begin to see it as a complex landscape where different civilizations achieved different peaks of knowledge, where progress in one area sometimes meant regression in others, where wisdom was gained and lost, and sometimes regained. The ancients were not stupid. They were not primitive. They were humans as intelligent as we are, solving problems with the tools and knowledge available to them. Sometimes they achieved solutions we have yet to match. Recognizing this does not mean romanticizing the past or rejecting modernity. The Romans also made terrible concrete when they did not follow best practices. They built structures that collapsed. They faced disasters and failures. The difference is that their successes were so spectacular that they outlasted their failures by millennia. What we can learn from them is not just technical knowledge about volcanic ash and lime, but something deeper about the nature of excellence, durability, and building for posterity. The Romans built as if their works would last forever. They used materials they knew would endure. They employed techniques they had perfected over generations. They created structures so over-engineered, so robust, so well-conceived, that they continued functioning long after the empire that built them had vanished. Modern construction rarely operates with such long horizons. We build for economic lifespans measured in decades. We optimize for initial cost, not lifetime value. We accept obsolescence as inevitable. What if we did not? What if we approached construction with Roman ambitions? What if we built harbours designed to last 2,000 years? What if we erected buildings that would awe and inspire people in the year 4000 AD? This is not just nostalgia for an idealized past. This is a radical reimagining of our relationship with time, with material culture, with the legacy we leave to future generations. Some modern architects are already thinking this way. Japanese temple builders maintain traditions stretching back over a millennium, with techniques designed to allow structures to be rebuilt exactly, endlessly, forever. European cathedral stonemasons still use methods refined over centuries. Traditional Moroccan builders work with lime plasters that cure slowly over years to create surfaces that improve with age. These are not primitive throwbacks, but sophisticated alternatives to the disposable modernity that dominates contemporary construction. The rediscovery of Roman concrete is catalyzing a broader conversation about these alternatives. It has become a symbol for lost knowledge, forgotten wisdom, and the possibility of rediscovery. But it also reminds us that knowledge is precious and fragile, that civilizational collapse means more than political and economic disruption. It means the severing of knowledge chains that may take centuries to reconnect. In 2023, Marie Jackson published a comprehensive analysis of Roman maritime concrete that may represent the most complete understanding we have yet achieved. Her work synthesizes decades of research across multiple disciplines: geology, chemistry, engineering, archaeology, history. Reading her papers is like watching a puzzle finally come together. Each piece of evidence, mineral compositions, isotopic analyses, historical texts, archaeological context, fits into an increasingly clear picture of what the Romans achieved and how we might build upon their foundation. But Jackson is careful to note that we still do not fully understand everything. There are subtleties in the material that continue to puzzle researchers. There are variations between different Roman sites that suggest they use multiple formulations for different circumstances. There is evidence that they continued experimenting and improving their techniques over centuries. In other words, Roman concrete was not a single invention, but a continuously evolving technological tradition. It was alive, in the sense that living crafts are alive, passed from master to apprentice, refined through practice, adapted to local conditions, responsive to new challenges. This is harder to revive than a simple formula. You cannot just write down the ingredients and proportions and expect to recreate what took the Romans centuries to perfect. You need to rebuild the tradition itself, the embodied knowledge, the practical wisdom, the community of practitioners who understand the material intimately. Some researchers are attempting exactly this. They are not just analysing ancient concrete, but trying to work with it as Roman builders did, mixing it by hand, learning to judge consistency and quality by eye and touch, building test structures using ancient tools and methods. This experimental archaeology is revealing insights that laboratory analysis alone cannot provide. It turns out that the physical act of mixing and placing the concrete teaches you things about the material that you cannot learn from chemical formulas. The Romans knew these things intuitively because they did it every day. Modern researchers must rediscover them through painstaking practice. But slowly, the knowledge is returning. And as it returns, it brings with it a profound shift in how we think about building, about materials, about our relationship with the deep past and the distant future. The Pantheon still stands in Rome, its dome still perfect after 19 centuries. Every day, thousands of visitors pass beneath it, most unaware that they are witnessing evidence of knowledge that we forgot and are only now reclaiming. That dome is not just a tourist attraction, it is a message across time, a demonstration of possibility, a challenge to our assumptions about progress, a reminder that the ancients, at their best, achieved wonders that we struggle to match even with all our advanced technology. But it is also a beacon of hope, because if we could forget how to do something this magnificent and then rediscover it, what else might we reclaim? What other lost knowledge waits in ruins and archives, ready to solve problems we face today? The revelation of Roman concrete's secrets is not an ending. It is a beginning, the start of a new relationship with ancient wisdom. The opening of a door we had thought permanently closed. Beyond that door lies not just better building materials, but a different way of understanding human knowledge itself, as something that can be lost and found, forgotten and remembered, that flows not in straight lines, but in cycles and spirals, returning to wisdom that we had left behind. The Romans are speaking to us across 2 millennia. They are telling us that we are not as advanced as we think, that our ancestors were not as primitive as we assumed, that building for eternity is possible. Are we listening? Eternal foundations. As our journey comes to its close, let us stand once more at the threshold between past and future, between what was lost and what might yet be found. We began in the shadow of the Pantheon, contemplating a structure that should not exist, a concrete dome built without modern technology, without scientific instruments, without the benefit of 2,000 years of subsequent knowledge. Yet there it stands, perfect and complete, mocking our assumptions about the direction of progress. We travelled backward through time to volcanic fields where the earth itself seemed to whisper secrets about materials and transformation. We watched Roman engineers discover that volcanic ash mixed with lime could create something stronger than stone, more durable than bronze, more permanent than memory. We witnessed the rise of an empire built quite literally on this foundation, harbours that enabled naval supremacy, roads that connected a world, aqueducts that carried water across mountains, buildings that inspired awe then and still inspire it now. And then we watched it all vanish. Not destroyed by conquest, many Roman structures survived the barbarian invasions. Not eroded by time, the concrete endured even as empires rose and fell around it. But forgotten. The knowledge dissolved like morning mist, leaving only the evidence of its own impossibility. For 1,000 years, we walked among ruins we could not replicate. We studied texts we could not fully understand. We measured buildings we could not rebuild. The answer was right there, written in concrete and stone, but we lacked the language to read it. until now. The rediscovery of Roman concrete's secrets is one of the great detective stories of modern science. It required electron microscopes and X-ray diffraction, mass spectrometry and computational chemistry. It needed researchers who could bridge multiple disciplines: archaeology and engineering, history and chemistry, observation and analysis. What they found rewrites our understanding not just of ancient construction, but of human knowledge itself. The Romans, working without benefit of modern science, created a material that is in crucial ways superior to what we use today. They did this through observation, experimentation, craft tradition, and generations of accumulated wisdom. They did this by paying attention to volcanic ash and seawater, by noticing what worked and refining it obsessively, by building with ambitions that stretched across centuries. They left us a message in molecules, a testament in Tobermorite, a legacy that literally grew stronger with time, waiting for us to become wise enough to understand what we were looking at. And now we are beginning to understand. The implications ripple outward like waves from a stone thrown into still water. Practical implications for how we build in the 21st century. Environmental implications for reducing carbon emissions from cement production. Economic implications for creating infrastructure that lasts generations instead of decades. But deeper than any of these practical considerations is something more profound, a shift in how we relate to the past and future. We are not the pinnacle of human achievement. We are not the apex of a linear progression from primitive to advanced. We are simply one moment in the long story of human ingenuity, one chapter in a book that began long before us and will continue long after. Sometimes earlier chapters contain wisdom that later chapters forgot. Sometimes the ancients knew things we do not. Sometimes progress means recovering what was lost, not just inventing what is new. The story of Roman concrete teaches us humility. It reminds us that our ancestors were not stupid, not primitive, not limited by lack of intelligence. They were limited only by the tools and frameworks available to them. And within those limitations, they sometimes achieved miracles. It also teaches us hope. Because if we could lose such magnificent knowledge and then rediscover it, nothing is truly lost forever. Every ruin holds secrets. Every ancient text contains clues. Every traditional technique might solve problems we face today. The question is whether we have the wisdom to look backward as well as forward, to learn from the past as we build the future. Standing in the Pantheon, feeling the weight of 2,000 years of history pressing down through that perfect concrete dome, we face a choice. We can dismiss this as a curious historical anomaly, interesting but irrelevant to modern construction. Or we can see it as what it truly is, a challenge and an invitation. A challenge to our assumptions about progress, about the superiority of the new over the old, about the direction of human knowledge. An invitation to rediscover what we have forgotten, to rebuild lost traditions, to reconnect with wisdom that transcends the brief span of our individual lives and connects us to the long arc of human civilization. The Romans built for eternity, not because they knew their structures would last 2,000 years, though they did, but because they refused to build for anything less than their highest aspirations. They approached construction as an art, a science, and a sacred trust with future generations. What if we did the same? What if we built our world as if it would be inherited by people we will never meet, in centuries we cannot imagine? What if we approached our work with the same ambition that led Roman engineers to pour concrete into Mediterranean waters, confident it would outlast empires? This is the lost blueprint. Not just a formula for volcanic ash and lime, but a framework for thinking about human achievement, about legacy, about the responsibilities we bear to both past and future. The past is not dead. It is not even past. It lives in every structure the Romans built that still stands. It speaks through every technique we rediscover. It challenges us through every ancient accomplishment that we struggle to match. And the future? The future is being poured right now, in the foundations we lay, in the materials we choose, in the ambitions we hold or abandon. Will we build for eternity, as the Romans did? Or will we build for obsolescence, for profit, for the short term and the quick return? Will we reclaim lost knowledge and integrate it with modern understanding? Or will we dismiss the past as irrelevant and continue severing ourselves from traditions that could make us wiser? These are not abstract questions. They are being answered every day in every building that rises, in every infrastructure project, in every decision about materials and methods and meaning. The Pantheon stands as eternal witness. The Roman harbours beneath Mediterranean waves continue their slow, crystalline evolution. The aqueducts stride across the countryside, carrying no water now, but bearing still the message of their makers. They are telling us that greatness is possible, that durability is achievable, that building for the ages is not naive romanticism, but practical wisdom. They are reminding us that we stand on foundations we did not build, that we inherit knowledge we did not create, that we are custodians of traditions that began before us and must continue after us. And they are challenging us to be worthy of this inheritance, to reclaim what was lost, to build what will endure, to leave behind not ruins and waste, but structures and knowledge that will inspire wonder 2,000 years from now. The lost blueprint has been found. The forgotten formula is being remembered. The ancient knowledge is being rediscovered. What we do with it, that story is still being written. In the ruins of Portus and Caesarea, in the dome of the Pantheon, in the electron microscope images of aluminum Tobermorite crystals, the Romans are speaking to us across the abyss of centuries. They are telling us that what seems impossible is often merely forgotten, that what appears primitive may be sophisticated beyond our understanding, that the answers we seek sometimes lie not ahead of us, but behind us, waiting to be rediscovered. Listen carefully to those whispers from the past. Look closely at those ancient structures. Study deeply those lost traditions, because somewhere in the accumulated wisdom of our ancestors lies the key to challenges we face today. Somewhere in the ruins of civilizations past are blueprints for civilizations future. The Romans knew how to build for eternity. Do we? That is the question their concrete asks us 2,000 years later, still strong, still standing, still waiting for an answer worthy of its endurance. The lost knowledge has been found. The ancient science has been revealed. The blueprint has been recovered. Now comes the hardest part, living up to it. This is not the end of the story. It is the beginning of a new chapter. A chapter we are writing now, with every choice we make about how we build, what we value, and what we choose to remember or forget. The Romans left us more than structures. They left us standards, standards of ambition, of durability, of thinking beyond the moment to the millennium. Can we meet them? The concrete still standing after 2,000 years says it is possible. Now we must prove it is so. The camera pulls back slowly, rising above Rome as the sun sets, the Pantheon's dome catching the last light of day, still perfect after 19 centuries, still testifying to knowledge lost and found, still standing as challenge and invitation to every generation that walks beneath it. Fade to darkness. But the knowledge remains.